All right, so I would like to continue from today's lecture. Like I said, it was a little bit too much for me to cover, like a little bit too much, I would say. But definitely I want to cover everything. So, for example, we talked about the transpose of a matrix, and we have seen an example of this property, right? Property number 4, right? If I have two matrices, then AB transpose is B transpose A transpose, and we have seen it. We've seen that this property is valid through these two matrices. Now, um, I will also want to talk about something else. Okay, let me give you another example. For example, so another example is the product of a matrix. So this concerns the product of a matrix, and its transpose, right? So for example, let me consider the following matrix. For the matrix, let's just take A to be 1, 3, 0, -2, -2, -1, right? Find the product AA transpose. So we can multiply the matrix by its transpose and show that it is symmetric, and show that it is symmetric. And I'll explain immediately what symmetric means. Well, first of all, let's compute this. So first, but before we start computing this product of A and A transpose, I want you to tell me what is the dimension of A? So let's write it. A transpose will be 1, 3, 0, -2, -2, -1 times the transpose will be the same matrix, but it will be 1, 0, 1, 0, -2, and 3, 2, -3, -2, -1. Okay. So this is A and this is A transpose. So matrix A is of what size?
A 3 by 2.
3 by 2, right? So I have 3 rows, 2 columns, and the transpose will be a 2 by 3. So the product, guess what? The product will be what? What kind of matrix will be?
A 3 by 3.
3 by 3 matrix. And it will be easy to see that once we multiply these two here, so we'll have 1 times 1 plus 3 times 3, which will give us 10. Okay, let me just write it. So this will be 10, -6, -5, -6, 4, 2, and the last one will be -5, 2, and 5. Okay, so this is a 3 by 3. Now, I want to show that this matrix is symmetric. A transpose is symmetric. So the question is, what is a symmetric matrix? That is the question I want to answer. So this means, you know what, a matrix is symmetric if and only if it equals its transpose. So in our case, so X is symmetric if and only if X equals X transpose. So in our case, we need to show that. So in our case, we need to show that what? That AA transpose is the same as AA transpose and everything transposed, right? So what do you think? So if we transpose, so let's look at the matrix again. AA transposed, AA transposed, everything transposed. If we look at this matrix here, right? Look at it. It's this one, the 3x3 matrix. So let's transpose it. You see that it's the first row is the same as the first column, so there is no problem. The second row is the same as second column, and the third row is the same as the third column. So whenever you transpose them, there is no problem, right? So basically it's going to be the same thing. So it's going to be 10, -6, -5, and -6, 4, and 2. -5, 2, and 5. Okay. So this implies that indeed AA transpose is symmetric. Okay. Now, so we've talked about the transpose of a matrix. We've talked about the null matrix, the identity matrix. We have seen that the fact that in general the multiplication of matrices is associative, but not commutative, not always commutative. So you can always find matrices such that A and B, such that A commutes with B, but also you can find matrices such that A does not commute with B. So in other words, you can find matrices AB such that AB equals BA, but you can also find matrices such that AB is not BA, and we have seen an example in the previous lecture today. Okay, now I want to talk about something else, the inverse of a matrix. We want to see when we can compute the inverses of matrices, whatever that is. And unfortunately, this is one of the things that I don't like to do before I talk about the determinant of a matrix, but this is how the book does it, so we're gonna follow the book. So here I'm interested in finding the inverse of a matrix, provided that that inverse exists. Then I also want to use the properties of the inverses of matrices, and also the final goal will be how to use the inverse of a matrix to solve systems of linear equations. So now I have more tools to solve systems of linear equations. But before I go and talk about matrices and their inverses, let me draw your attention. So let's talk about the first thing, matrices and their inverses. Right? So before I go and talk about it, let me draw your attention. Let's consider the following, the real equation. Since you have learned this in middle school probably, AX equals B. Do you remember this? Where A and B are real numbers. Let's see. Do you remember how to solve this? So how did you solve this? You divide by A, and then you'll say that X equals B over A, but there is a problem. Can you divide always by the real number A? What do you think?
No, because if B is a 0, then you can't, it's going to be, you're just going to delete the equation.
If what, B is 0? I don't think I have problems with B being 0. I have a problem with A being 0, right? So if A is 0, then I have B equals 0. So there is nothing to, I have 0 equals 0. So I can always divide by a number to form a fraction as long as the denominator is non-zero, right? So to solve this equation, and I'm going to do it in the form, okay, so if A is not 0, then I can divide by it. I can say that x equals B over A is a solution to the equation, to the above equation. Right? I can say that, but provided that I have this. Okay, so that's the solution, provided that A is different than 0. But let me write it in a little bit different, in a different language. Let me take again, AX equals B. So now, provided that A is different than 0, I can multiply by A inverse here to the left. So first step, multiply by A inverse, so in which in our case is 1 over A, to the left. So I'm showing you this procedure, which is, you take it for granted, but so that you can see how we're gonna apply it when we deal with matrices. So once we multiply by this to the left, okay, this I need to make sure provided that A inverse exists, so that 1 over A exists. Provided that, so this means provided that A is different than 0. All right, so once I have this, so I will have A inverse times A times X equals A inverse times B. Okay. Now, since the multiplication of numbers is associative, this will be equivalent with A inverse times A times X equals A inverse B. Well, this guy will give me the identity, right, which is 1. And this will be equivalent with saying that 1 times X equals A inverse B. 1 times X is X, so this is equivalent with X equals A inverse times B. And that's the solution of the equation. So you see, I've performed here more steps, but it's still the same solution. So this is nothing else than just B over A. You see, you take it for granted when you deal with the real numbers, but for matrices, that's the language we're going to use. So now let me talk about the definition of the inverse. So definition. The inverse of a matrix. So it says the following, and I'm going to emphasize something here, an n by n matrix A is invertible if there exists a matrix, or sometimes we call it, in fact, sometimes we call this non-singular. Sometimes it's called non-singular. When there exists an n by n matrix B such that, guess what? The two matrices commute, and not just that, they're equal to identity, such that AB equals BA and equals the identity. That's the condition. And in this case, where, of course, where IN is the identity matrix, is the identity matrix, right? And we say that, in this case, we say that B is the multiplicative inverse of A. So basically, when we denote this by, we'll write it like this. Anyway, B equals A inverse. A to the negative 1, the inverse of A. And that's it. Right? So this is the inverse of A. And I want to point out, okay, before I point out the remark here, a matrix that does not have an inverse is called a non-invertible matrix. Non-invertible or singular matrix. Anyway, you'll see next week when we'll talk about that there will be a criteria for a matrix to be invertible, which will involve the what we will call the determinant of a matrix. So we're not going to use that in today's lecture. Now, let me point out the remark because I want to answer the following question. When do all matrices, or question, do all matrices have inverses? That is the question I want to answer. What do you think? What does your intuition say?
Not all of them necessarily have inverses.
Say that again.
That not all of them have inverses.
Not all of them have inverses, right? So, and what kind of, well, since not the answer, not all of them. The short answer. Now, but the question is, which ones have inverses?
Only
And
if they have determinants.
well, we're not going to talk about determinants yet. We'll see that, okay, since you brought it up, so whatever that determinant means, those matrices that have determinant 0 will be called singular or non-invertible. All others will be called invertible. But anyway, before I go into that, I want to point out the following remark. Non-square matrices do not have inverses. This is very important. I cannot talk about the inverse of a matrix unless that matrix is a square matrix. Okay. Of course, if the inverse, there is a theorem. If the inverse exists, of a matrix, exists, then it is unique. This is very important. There is only one, right? And now I'm going to give you an example of, okay, let me give you an example, which will tell you exactly how we show that a matrix is the inverse of another matrix. So an example is the following. Show that the matrix B is the inverse of A. And here we have A to B. So I'm going to take just 2 by 2 matrices, -1, 2, -1, 1. And B is 1, -2, 1, -1. So this is 1 here. Okay. How would you approach this? So based on the definition, what do we need to show? Let's go back to the definition. We need to show this, you see? Look at it. So we need to show that AB is the same with BA, and moreover, when you multiply the two, we'll give you the identity. So let's do it. In fact, I would like you to do it for a couple of minutes. Think about it, and we'll. So what is this? So this is -1, 2, -1, 1 times 1. You tell me what is this, and also this one is 1, -2, 1, -1, and -1, 2, -1, 1. And this will have a 2 by 2, and the same we'll have here, 2 by 2 matrix. And I want you to tell me which one is which one. So, what is AB? Say it, say it. Did it, when you multiply, do you have the identity there? Well, when you multiply these two, what do you have? Do you have -1 times 1 plus 2 times 1, which will give us 1? Then you'll have -1 times -2, which is 2 plus 2 times -1, which will give us 0. Then the same here will have 0. This will have 1. Wow, it's the identity. And guess what? The same thing will happen for when you multiply the other way around, BA, right? So you'll have also 1, 0, 0, 1, which is again the identity. So you can say that. So this implies that B is A inverse. So B is the inverse of A. But wait a second. Here you can argue that, all right, you told us to show that this matrix is the inverse of this matrix. But what if you give us a matrix and you ask us to find the inverse of that matrix? How do we do without telling that, without saying anything about the other matrix that will be? You see here in this example, it's quite clear what's going on. It says directly, show that this matrix is the inverse of this matrix, right? So B is the inverse of A. But what if I'm giving, so what if I ask you the following question? Given matrix A, just the way it is, as you can see it, -1, 2, -1, 1, find A inverse. How do we find A inverse? So we're gonna address this question, and you will see it next time. It will be a direct way of finding these matrices. It will involve what we will call the adjugate of a matrix. But anyway, we'll see about that next week. So now let me give you another example. Example 2, let's say. So finding the inverse of a matrix. How to find the inverse of a matrix. So in other words, find the inverse of matrix A, which is given by 1, 4, -1, -3. But you know what? What is the question that you need? I need to address before even look at the statement. Find the inverse of A. But what is the question before I even go and find the inverse of A? What is the question I need to address in the first place?
If it's even a square matrix.
Well, the matrix, as you can see, it's a square matrix. So if the inverse will exist, then definitely will be a square matrix. So I don't have any problems with that. What would be the problem that might appear in this? Well, the first question I need to answer is, does the inverse actually exist? You see, find the inverse of this matrix, but nobody can guarantee that this inverse actually exists. So the first question I need to answer, does the inverse of A exist? That is the question I want to answer first. And unfortunately, there is a way of showing this, but in fact, the answer at this point is a little bit complicated in the sense that, well, the answer is yes. But how? How do I show? Well, this is what we call the determinant of A that we'll learn next time. So I'm gonna abuse a bit the material and say something in advance of the matrix A. And in other words, the determinant will be computed in the following way. You're going to take, this is the main diagonal. You're going to multiply the elements from the main diagonal, and you're going to subtract the product of the elements from the secondary diagonal. So this will be, in general, so let me write it. If I have A11, A12, A21, A22, it follows that the determinant of A is A11, A22 minus A12 times A21. So that's the determinant. If the determinant is 0, if this number that A, so this is a number, is different than 0, then I can infer that A is invertible. Right? Okay. So in our case, we can compute this So let's do it. So if we compute this, so in our case, the determinant of A is nothing else than just 1 times 3 minus 4 times -1. But here it will be 3 plus 4, which is 7. And a 7 is different than 0. Okay, so the matrix is invertible. All right, but the question is, well, we answered the first question. Does the inverse of A exist? Yes, it does. But now the second question that I want to answer, how to find A inverse? And we're going to do it the hard way now. And you'll see what I mean by the hard way. So let's answer this. To find the inverse of A, we need to solve the following matrix equation. And the matrix equation is AX equals the identity for X. And we need to solve this for X. Right? So what does this mean? This means, let's write it. So this will be equivalent of writing 1 for -1, -3 times X will be X11, X12. By the way, these are 2 by 2 matrices, so that we X21, X22 equals the identity 1, 0, 0, 1. And once we multiply these, we can equivalently, this will be nothing else than just, if we multiply, so if we perform the usual matrix multiplication, we'll derive the following. So let's do it. So we have 1 times x11 plus 4 times x12. So the first will be x11 plus 4 x12. The second element from the first row will be x12 plus 4 x22. This, then you will have negative x11 plus minus 3x21. And the last one is negative x12 minus 3x22. Right? And this will be, has to be equal with 1, 0, 0, 1. And now we can identify, because we know what it means for two matrices to be equal. So their elements must be equal. So this will be equivalent with, so we equate the corresponding entries of the two matrices, and we obtain, guess what? Two systems. S1, let's write it, will be x11 plus 4x21 equals 1, and negative x11 minus 3x21 equals 0. And the second system, and S2, let me write it here, will be x12 plus 4x22 equals 0, and negative x12 minus 3x22 equals 1. Okay, so these are the two systems. We need to solve them. Anyway, I'll leave the details to you. So solving these details. So solving the system one, we'll get the solutions x11 equals -3 and x21 equals 1. And solving the second system, so you see it's a little bit of a pain to solve these. We derive that x12 is -4 and x22 is 1. But no problem. So I have these two solutions for each system. But and at this point, I can write that what? That my matrix A, so if you look here, so this implies that AX equals the identity. If I multiply by the inverse to the left, this implies that A inverse times A times X is A inverse times the identity. But A inverse times the identity, we know that it's A inverse. So any matrix multiplied by the identity will give you the matrix. So this implies, and these guys here, A inverse times A is nothing else than the identity. So this implies that X equals A inverse. So that's the solution. You see? By just solving this. So in our case, this means that it's also given by the following matrix. So these are the solutions of the two systems. So x11 is -3, x12 is -4, then x21 is 1, and x22 is 1. So that's the inverse. Wow. Not very practical, isn't it? And imagine that we're lucky here because we only had 2 by 2 matrix. And that's not very practical. Imagine if we have a 3 by 3. We'll go nuts if we have a 3 by 3. So, so imagine for 3 by 3, probably we'll have 3 systems of of linear equations with 3 equations each. So that's not going to be very pleasant, right? So this is the hard way of doing things. I wanted to show this because I don't want you to apply this method again. That's why I wanted to do it. I did it on purpose. But now, maybe there is another way of finding the inverse. And the way we find the inverse is, and I'm going to give you another example with 3 by 3 matrix. But before we go into that, let me give you, okay, let me answer this question. Is there another nicer way of finding an inverse, of finding the inverse of a matrix? And well, since we've talked about the augmented matrices, coefficient matrix, row echelon form, why not apply it in this case as well? So let me describe you the procedure. So the answer is yes. The short answer, yes, definitely. And let me just like I said, let me describe how to find the inverse of a matrix. So the procedure is the following. So let A be a square matrix, and I want to emphasize on this, this is very important, a square matrix of size n, let's say, right? And the first step is the following. Write, and here I want you to pay attention, n by 2n matrix. This is very, very important. That consists of A on the left on the left, and the n and the n by n identity matrix on the right. So this is very important, on the left and on the right. Anyway, to obtain, you'll see how it will look like to obtain, and we'll write it in this way: A times AI. This is called, this process, this is called adjoining the identity I to the matrix A. Okay. So that's the first step. So we need to write that. The second step, if possible, row reduce. This is very important. So basically, we're just going to apply the elementary transformation to derive the row echelon or row reduced echelon form. So row reduced A to the identity using elementary, just like I said, using elementary row operations on the entire matrix and AI. So that's what I'm going to do. I'm going to apply the row using elementary row operations on this matrix AI. And the result will be the matrix, and let me write here with a different color. Identity, and here I'll have the A inverse. That's the amazing thing, right? So I'll have the identity inverse. Okay, if this is not possible, okay, then A is non-invertible, or we call it singular. And now the last step, because if we want to check if it's correct what we did, the last step, check your work by verifying the equality A times A inverse is the same as A inverse times A, and it is the identity. That's it. This is what we need to do. That's the procedure. You see, there are 3 steps: 1, 2, and the third one is just to check if your work is right or not. Right? Okay. So we need to let's give an example. So an example on how to find the inverse of a matrix. So I can do the 2x2 previous matrix, but I want to do another example. let me do, let's say a 3 by 3 matrix. So example, find the inverse of the matrix. And let's take the following matrix. A is a 3 by 3. It's 1, -1, 0. Then 1, 0, -1. And the last one is -6, 2, and 3. Okay, so this is a 3 by 3, so it's a square matrix, so definitely I can find the inverse. But now here comes the question again, and that's why I don't like talking about the inverse of matrices without talking about the determinant. So the first question I need to address will be what? Which one? If the inverse actually exists. Okay, it actually it does exist, or we will assume that. But now let's apply the procedure, assuming that so we assume that the inverse of A does exist. Big assumption. Huge assumption. Okay. Okay. All right. So assuming that, let's form, let's adjoin the identity matrix to the matrix A. So we'll have A, the identity. So write it. This is it's going to be a big matrix. It will be what kind of? So it will be a 3 by 6, right? Because we said here, you should check. Step 1, write the n by 2n matrix that consists of A, look here, n by 2n matrix that consists of A on the left and the n by n identity matrix on the right to obtain AI. So basically we adjoin the identity to the matrix A. Okay, let's do it. So once we write this, so let's write the matrix A. So it will be 1, -1, 0, right? And let me put it like this so here I have the identity so that it's clear, right? So this is the part where the identity is. And this is the part where the matrix A is. So that's what we call AI. All right, so it's 1, -1, 0, 1, 0, -1. And the next one is -6, 2, and 3. Okay. So so this is how we adjoin the identity to the right of matrix A. And what I want to do, my goal is, so keep in mind what your goal is by performing elementary operations, elementary row operations, so that will be specific. We want to obtain a matrix of the form keep in mind we want the identity here on the left, and here on the right we want A inverse. So that will be the inverse. Okay, so let's do it. Let's write it. So keep in mind I want to perform the same type of elementary row operations, so that such that I'll have leading ones starting from the left, zeros underneath the leading ones. And once I have this, then I can stop and say that that's the inverse of my matrix. So let's do, okay, what operations would you suggest? So my first goal is to, so this is the leading one here, right? I want the one beneath, underneath that leading one to transform into 0. So what kind of operations would you suggest?
Multiply row 1 by -1 and then add that to row.
Add it to R2 to obtain a new R2. So let's do this. So we'll have the following. So this will be equivalent with the following matrix. So the new, so let's copy. So let's keep in mind here. So R1 will stay the same. And the new R2 will be -1 times R1 plus R2 will be the new R2. Okay. So the first one, let's copy it. 1, -1, 0. 1, 0, 0. But now, and let's copy also the R3 will stay the same. So -6, 2, and 3, and then 0, 0, 1. And now the only thing that we're going to modify will be R2. So you will have what? 0, 1, -1, right? And here you will have -1, 1, 0, correct? Please correct me if I did something wrong here. Right? Okay, now I have a 0 here. Why not? And I'm lucky because you look, I have 1 here. I have a 1 here. Perfect. Maybe I should do something to get rid of this -6. So what would you suggest? What kind of other operations would you suggest to do on the third row, basically? So R1 and R2 will stay the same. So let's copy them. 1, -1, 0. 1, 0, 0, 0, 1, -1, -1, 1, 0. And now on the third row, what kind of operation do you suggest?
I was going to ask, on the 5th column, is that supposed to be a 0 instead of a 1?
0. Which the last one?
5th column, second row.
The second row here.
So it's
so
no,
it's 0, 1, -1, right? Where do you have a problem?
No, so it's the 0, 1, -1, -1, and then shouldn't that be a 0?
0, 1, -1, and instead of this -1 here on the right is 0.
The one next to it, just the positive one.
This one here should be 0.
Yeah.
Let's see. Yeah, maybe I did a mistake. Let's see. So I said that -1 times R1, and you add it to R2. -1 times R1, and you add it to R2. No, it's, oh, look. No, it's 0 plus 1. Yeah, which is 1. What's the problem?
Oh, sorry, I was thinking something else. Sorry.
No, it's correct. It's correct. No, that's the way it should be. Okay. Now, R3 will be modified. So what would you suggest to do? Keep in mind that I want to get rid of that -6. I want to obtain a 0 there.
Multiply R1 by 6.
Multiply R1 by 6 and what else?
Add it to row 3.
Exactly. That will be my new R3. All right, so what are we going to get? Will be 0 here. That's exactly my purpose. Then the next one will be what? -4, correct? Please correct me if I'm doing wrong. 3, 6R1 plus R3, 6, 0, and 1, right? Okay, then that's great. Keep in mind what we want to do. Don't forget about our purpose. We're trying to make this a matrix on the left to make it look like the identity matrix. We won't stop until we get there. So the only thing we need to do to transform everything else into a 0 and leave the main diagonal and to transform it into 1. So what else should I do? Maybe I could turn that -4 on the third row into a 0. What do you think? What should I do? Is this -4 here? So what do you think I should do?
Multiply the second row by 4 and add it to row 3.
Exactly. So R1 and R2 will stay the same. I'm going to copy them just the way they are. So it will be 1, -1, 0, 1, 0, 0, 0, 1, -1, -1, 1, 0. And R3 now, we said 4 times R2 plus R3 will become the new R3. Okay. So that will be what? Will give us what? Will be 0, 0, -1, 2, 4, 1, right? Now, let's see, what should we do? Maybe we can transform this -1 here to make it look like a 1. So I could do the following. So I can multiply the third row by -1. So I'll have 1, -1, 0, 1, 0, 0. So this is R1. This is 0, 1, -1, -1, 1, 0, R2. And the last one, we said that we're gonna perform the following. -1 times R3 will become the new R3. So this will be equal to what? 0, 0, 1. Not this is 1 here. -2, -4, -1. Perfect. Now, keep in mind that I have left, everything is nice here on the main diagonal. It's exactly what I want. The only problem I have is with these two -1s. So I have to turn them into some zero. So I have to be very, very careful when I'm doing this. So what would you suggest?
R1 plus R2.
Add R1 plus R2 to what? To transform it to be a new what? R1 or R2?
R1.
You sure? Maybe R2.
Okay, R2.
Anyway, it doesn't really matter. You can, so R1 to R2 to be the new R2. So let's do this. So I'll have R1 will stay the same. So it's 1, -1, 0, 1, 0, 0. And now let's pay attention. So I'm gonna add, you said R1 plus R2 to become a new R1. Actually, you're right. Okay, you know what? I'm gonna do it afterwards. So let me do the following. R2 plus R3 here now to become the new R3. R2, sorry. And then we're gonna perform the last one. So let's copy. So this will be 0, 0, 1, -2, -4, -1. And now let's see, the second row will be what? 0, 1, 0, right? And here we'll have -3, -3, and 1. And -1, sorry. And now, just like Mariah says, we're gonna do a last operation. So we're gonna do R1 plus R2 to become the new R1. R1 plus R2 to become the new R1. So R2 and R3 will stay the same. So we'll have the following. Yeah, R1 because I'll have 1, 0, 0. Then I'll have what? -2, -3, -1. Here I'll have 0, 1, 0, 0, 0, 1. Pooh, perfect. -3, -3, -1. -2, -4, -1. Guess what? What should I do now? Should I stop? Why not? So if I stop, this is just the identity. And this is just the inverse. That's the inverse of the matrix. Well, the inverse, so the inverse of A is given by A inverse is equal to this matrix that we just said, -2, -3, -1, -3, -3, -1, -2, -4, -1. That's it. That's how we find the inverse. Well, I will leave it to you as an exercise to check the final step. Check that A inverse is the same as A inverse times A and is the identity. I will leave it to you as an exercise to do this. You just multiply A by A inverse, just like we previously did for that 2 by 2 matrix. Also, I would like you to look at the notes. So in example 4, so I'll leave it to you, example 4, see the notes, see the lecture notes, page, I think it's page 31, 32. Well, it will give you an example of a matrix that has no inverse. And when you will see that, so you'll try to perform the same thing. And then at some point after doing elementary operations, you'll obtain a row of 0 on the left. Then you will stop. That portion will tell you that A has there is no chance for you to obtain an inverse. So therefore, that matrix will be singular. In fact, this is one of the properties of the determinants as well. So I'm not going to go into that now, maybe next time. Now, I want to talk about the properties quickly, about the properties of, and maybe I should say a few words about elementary matrices. So properties of inverses. So just like the transpose of a matrix, there are some properties of inverses. So if A is an n by n invertible matrix, let's say K is a positive integer. K is a positive integer. And C is a non-zero scalar. Then A inverse AK, A to the power K, right? I'm going to raise this to the power K. Then C times A, the scalar multiplication of a matrix, and the transpose, guess what? All of them are invertible. And the following hold true. So the following properties hold. The first one, Oh. So the first one says that A inverse and inverse, just like we did for the transpose, will get you back to the matrix A. The second one, let's say if we raise A to the power K and we want to compute the inverse of this, so this will be nothing else than just A inverse times A inverse times da-da-da, A inverse K times, right? So we have K factors, so this will be nothing else than just A inverse to the power K. The third property will be if I have a scalar times a matrix, so the scalar multiplication by a matrix, and I want to find the inverse of this, this is nothing else than just 1 over C times A inverse. Keep in mind that this is a scalar. All right, and last but not least, fourth one is A transpose inverse is nothing else than just A inverse transpose. So these are the properties. But also there is another property, and just like I said, which is similar to the one that we talked in the previous lecture about the transpose of a matrix. So there is a similar one for inverses, which says the following: AB inverse. So if I multiply these two matrices, A and B, if I want to multiply the inverse, is nothing other than just B inverse times A inverse. That's a very, very important property. Keep in mind this. Right? And just like I said, there is an example. I would like you to look for the example. So see, there is an example of finding. So see the example from the notes. Pages 36, 35, 36. Anyway. Okay. Now, towards the end of this, I want to say a few words about elementary matrices. And probably I'm going to stop here. Just a few words. And you will see more examples of elementary, how we deal with elementary matrices in my notes. Also, I will leave the LU factorization for next week's lecture, since it will involve a little bit of determinants as well. So I don't want to say something which involves determinants and try to avoid talking about determinants. So let's talk about a bit about elementary matrices. So what is the purpose of doing elementary matrices? So the final purpose is, just like I said, to find the LU factorization. So in other words, we want to write a matrix as the product of what we will call a lower triangular matrix and times a upper triangular matrix. But before we go into that, let me call the following definition. An n by n matrix is an elementary matrix when it can be obtained from the identity matrix in by a single row operation, by a, okay, let me write this, by a single row operation. Okay, let's see some examples. This is very important. So it's an n by n, it's a square matrix, and I can obtain it from the identity from this guy here. I can obtain it by a single row operation. So that's what we have to keep in mind. Before I go into this, let me ask you some examples. What do you think about the following examples? Let me take this matrix. A to B, 1, 0, 0, 0, 3, 0, 0, 0, 1. And let's say B is 1, 0, 0, 0, 0, 1, 0, 1, 0. What do you think? Which one of this is elementary? Which one is not elementary? Let's keep the definition here.
Would they both be elementary since you can multiply
Both elementary? Let's see the first one. Matrix A. What do you think? Is it elementary or not?
Yes, you can just
Why?
multiply. You can multiply row 2 by 1/3.
By 3, right? So you multiply the second row is elementary. How do we obtain this? Because it's obtained. It is obtained by multiplying the second row by 3. By 3. What about matrix B? What do you think? Is this elementary or not?
I think it would be just because you can switch row 2 and row 3.
If we, yes, it is. Yes. We just switch the second and the third row. I think I made a mistake in my notes. The second and the third row. I said it's not, but I don't know, I was thinking of something else. Okay, so what are these elementary matrices good for? And probably I'm just gonna give you the theorem and then I'll give you something to read on from the notes. So the following theorem holds true. So this concerns the representation, so representing elementary row operations. So it says let E be the elementary matrix obtained by performing an elementary row operation row operation on the identity, on IN. If that's if that same elementary row operation is performed on an M by N matrix A, then the resulting matrix, guess what, is the product EA. That elementary matrix times A. Well, you'll see an example to how to find a sequence of elementary matrices. So I will leave it to you as an exercise how to apply this theorem. See the example from the notes. Pages, I think it's 42, 44. In fact, 42, 47, if there are a bunch of other examples as well. Anyway, since I don't have too much time left and I don't want to talk about it, I think I'm going to stop here. Thank you very much. I will upload the video on YouTube and then I will send it to you afterwards. Okay, let me